Let us now continue our discussion on the integration of rational fractions. So we tackled last time the case 1, which is our denominator or our q of x is consists of distinct linear factors. So our denominator is in term of linear factors in form of ax plus b. So for case 2, we have now repeated linear factors. We're in our linear factors here, this is linear, is repeated by having power n. So our rule regarding this is that we will equate this as equal to a constant a1 to be determined all over ax plus b, this linear factor here, and then plus the another constant all over all over the ax plus b raised to 2, and will be repeated until such time that the power is equal to n. Okay, so for illustration of this application of the rule, say we have 2x minus 5 all over x squared by x minus 1 squared. Okay, so as you can see here, we have two groups of ax plus b. First one is this x squared, and we have x minus 1 that is also raised to 2. So what we will do here is to follow this rule. So we have a1, or let's call it a, all over the first linear, which is in terms of x, and then plus, let's say another constant is in terms of letter b, all over x, but it is now raised to 2, and we're in our n is equal to 2. That's why we will end here. Okay, and then so for the second part, we have plus another constant, let's call it c, all over x minus 1. Okay, so we have raised to 1 here, and then plus d all over x minus 1 squared. Okay, and we will also end here since our n is equal to 2. Right, so another illustration for this is that, say we have 2 y all over y minus 2 cube, right? So say we have this repeated linear factors. So as you can see here, our inside the parenthesis is linear and having n power of 3. That's why we have repeated linear. Okay, so our technique here is to first we'll equate this with a constant a all over y minus 2 raised to 1, or y minus 2, and then plus another constant, which is y minus 2 raised to 2, and we need to make this kind of equation until such time this will the power of this denominator on our factors will now be equal to 3. So we have c. Now we will end here since our third part is now equal to 3, and our n here is equal to 3, right? So this is 2, by the way. So this will become our equivalent fractions in terms of partial fractions. Okay, with the consisting of repeated linear factors in its denominator. So another illustration, say we have 10 all over y, say z squared z minus 1 to the 4. Okay, so we have two different linear factors, but it is now our n is equal to 2 and n is equal to 4. So our technique here is to make a form like this one. So we have a all over z raised to 1 plus b all over z squared, and we end up here for z raised to 2. But for z minus 1 raised to 4, we need to do 4 z minus 1 raised to 1 plus d all over z minus 1 raised to 2 plus e all over z minus 1 raised to 3 until such time that we've end our equation with z minus 1 raised to 4, because our n here is 4. So we need 4 different fractions here. Okay, so z raised to 2, we have 1, 2. For z minus 1 raised to 4, we have 1, 2, 3, and 4. So that is what we call the case 2, which wherein our denominator consists of repeated linear factors. So this will become a powerful tool to integrate this kind of integrand, to simplify this kind of integrand. Okay, so on the next video we will gonna discuss some or we will evaluate some examples regarding the case 2 of the integration of rational fractions, wherein the denominator consists of repeated linear factors.